1913. So he discovers the nucleus, and within 30 years, you have an atomic bomb. They didn't even know. And Rutherford was actually asked at the time. He said, so it's the usual question we get as physicists. They say, what's the use of this? And Rutherford said that there's no use to it. So anyone who thinks that you could use this as an energy source is talking moonshine. And within 30 or 40 years, you have nuclear reactors producing power, and you have atomic bombs. Rapid progress.
Well, that's one thing that's been constant about people and predicting the future. That we've always got it wrong. Always.
Yeah, we miss some of the rapid advances. You know, we talk about, there's a computer there and a phone here. The fact that in modern electronics is a single lifetime. The transistor is 1940s, I think, at Bell Labs here in the US. It's not long ago, that you go from that to this. I mean, we talked about the Apollo. I mean, this is significantly more powerful than anything that was available in the world when Apollo was there. The rooms filled of computers at NASA, which were nowhere near as powerful as that.
It's amazing. I mean, that's those Google glasses that people are wearing is a sign of things to come, in my opinion. They've stopped making them, but there's a new company that has like a goggle that looks like a skiing goggle, and it allows you to move things in front of you like a virtual desktop. You can spin squares, hold things in place, throw things to the side, and they disappear. I mean, we're going to get really, really, really weird within the next couple decades.
Yeah, I've actually seen some of that technology. It's a company called Magic Leap. I've been there in Miami.
You saw it in person?
Yeah.
What does it look like?
Really, it does indeed. You can put 3D objects into your field of vision. So
how is that working? So you've actually seen it.
I signed an NDA.
You did? You can't talk?
Yeah, but I tell you that it works. It's a remarkable thing.
Damn.
I think Google have just bought the company, actually.
We played it. We played some videos of it, and we couldn't figure out whether we were watching a simulation, we were watching what the future holds, or we're watching an actual demonstration of that technology.
Yeah. Oh, it's going to be impressive, I think. And it's interesting what you said, because it brings the web, this unlimited information into your field of vision, so you can manipulate it, and then there are questions about what's real and what isn't, and who cares anyway. Really, and it's an interesting.
Do you dabble at all in the theory of some sort of an artificial world that we live in? You know, these ideas of simulation. Do you dabble in that, or is it just too much?
It's interesting, actually. I mean, a colleague of mine at Manchester, there are some physicists who think that it's a possibility, a strong possibility that we're living in a simulation. I mean, it's speculative out there stuff, but it's an attempt to explain some properties of the universe that are interesting and unusual. So one of my favourite, I think, at the moment, piece of cutting-edge physics in cosmology, I should say, the study of the universe, the origin and evolution of the universe, is going through a revolution at the moment, and it's coming from data. So it's coming from measurements of things like the cosmic microwave background radiation, which is the oldest light in the universe. We're making it, so just to rewind and say what that is, 380,000 years after the Big Bang, the universe became transparent for the first time to light. And that's because it was cooling down, as it was expanding and cooling, then atoms formed. It became cool enough for atoms to form. And at that moment, very, very quickly, the universe becomes transparent, and so photons of light can travel on through the universe, and they've been doing so ever since. And we can take a photograph of that, and we have done, with a series of satellites, the most recent of which is called Planck, which is a European satellite that's up there. So this is a picture, a baby picture of the universe, as it was 380,000 years after the Big Bang. It's a very beautiful picture. But in explaining that, that's given support to theories called inflationary cosmology theories. So inflationary cosmology theories say that before the universe was hot and dense, which we tend to call the Big Bang, before that the universe was still there, and it was doing something else, which was an exponential expansion. So it was expanding exponentially fast, way faster than the speed of light. Then it stops, and all the energy that was causing that expansion gets dumped into space, heats it up, and that's what we see as the particles of energy today. So those theories are kind of interesting. But they also suggest that there are theories called eternal inflation theories that say, well, how long did that period of expansion go on for? And does it all stop at once, or does it stop in patches? And if it stops in patches, if it stops in a little patch, you'd get a Big Bang and a universe. If it stops in another patch, you get another Big Bang, another universe. So these theories suggest perhaps there are an infinite number, possibly, of big bangs, in inverted commas, which would mean there are an infinite number of universes like ours. And they're being created now, all the time, and they will continue to be created forever. So you get this fractal multiverse, ever growing exponentially fast. And really, bizarrely, those theories have some support from the cosmic microwave background. They're theories that explain the structures we see. I should just underline the fact that this is speculative in a sense, but it's relatively mainstream. But what one of my colleagues noticed, and some physicists have noticed, is if you were some kind of omnipotent deity programmer and you wanted to run what's called a Monte Carlo simulation to say, well, I'll vary the strength of gravity in one universe and vary the mass of the electron in another one, and vary these physical constants and see what happens, then this is probably the kind of thing you'd do. This is what it would kind of look like. So that you can make an argument that the universe, in some sense, looks like one of these kind of so-called Monte Carlo simulations, because it gives you the possibility of generating every possible number of different ratios of the strengths of the forces of nature and all these things. But I just have to emphasise, this is way out there, on the edge, but it's fun. And what is fun and interesting, though, is that the wind all the way back, the inflationary cosmology bit is probably the most widely accepted theory at the moment for how the universe got to be the way it is. And it does lend itself to this idea that there may be a multiverse. And it may be that in each different pocket universe, if you like, you can have different physical constants. So most of them wouldn't allow life to exist, but some of them would. So our universe looks very fine-tuned, if you look at it, in a sense. It looks like if the laws of nature were very slightly different, you wouldn't get carbon, for example, produced in stars in large quantities, which you need in order to, and when the stars die, the carbon and the oxygen come out and they relapse into another generation of stars and solar systems, and that's how you get the heavy elements that make up our bodies. And so all those things look, you either try and find an explanation for why the laws of nature are the way they are, or you go to one of these multiverse theories and say, well, actually, it goes back to what we were talking about earlier about the infinite monkeys. And actually, every possibility occurs in nature. And then we shouldn't be surprised that we live in a universe that seems fine-tuned for life, seems perfect for us to exist in, because every possible combination of the laws of nature exists somewhere. And this is where cosmology is at the moment. This is genuine. You could go onto the web and Google it. You'll find 1,000 review papers on what's called inflationary cosmology, and it is cool and interesting, actually.
Yeah, it's beyond that. It's very the idea of something being infinite, and not just infinite, but infinite numbers of these infinite things.
Infinite numbers of infinite universes. These theories exist.
So this idea of computer simulation, the idea that the world we live in, the universe we live in, is a simulation.
But that was the question that you first asked.
Well, no. It's because what you went on is beautiful. Don't change a thing. Stay you. The idea being that one day, if human beings continue to increase our technological abilities, one day we're talking about this magic leap, and we're talking about the goggles that allow you to see a virtual world. We're going to, if we don't blow ourselves up or get hit by an asteroid, we're going to come up with something that is indistinguishable from the reality that we see right now. And when people start examining the nature of the universe and they start looking at the fractal nature of things and looking at, like what you were saying, that if you were going to be some omnipotent deity that creates the universe, you'd probably do something like this. Every single combination and throw them out there. So when we discover, like is James Gates, that was the guy's name? Sylvester Gates. It was a guy who spoke to Neil deGrasse Tyson about string theory, and that they found in string theory this computer code that was created by humans in like the 1930s. They figured this out, and that this actually exists in these codes in string theory. And his idea was that somehow or another proves that there is some evidence support that life, the reality that we see right now, is a simulation. Or it could be that, which way more likely, that you're just discovering some sort of code that the entire universe is based on. That when you look at things being fractal and you look at the idea of there being not just infinite expansion but infinite contraction, and that there is no smallest point, there's just smaller than we can measure. But when we talk about subatomic particles and we talk about things being like atoms being mostly air,